Hello everybody. In this video we will discuss reaction of epoxide with a nucleophile such as alcohol in presence of a proton in acidic conditions. So what would happen if we have a nucleophile in acidic conditions? So in these type of problems you will see the H plus, whatever that source of H plus might be. Sometimes it might be written as sulfuric acid or some other H plus sources. Just keep in mind that both of these will be written like this together. There is no 1 dot 2 dot. If it's written like this, that means the reaction is a two-step process. So keep that in mind to differentiate. So there will be all of them, all the reagents will be written together. Okay, so what would happen in this particular scenarios? So we have oxygens with lone pair, and we know that lone pair loves proton. So immediately your oxygens, lone pair from oxygen, will abstract all the acidic proton that is available, right? So you will make the intermediate instantly. That looks something like this. So you get O H. Now oxygen has 3 bonds, so it will become positive, right? So 3 bonds means positive. And on the other side we got our CH3. So in this particular scenario, what is happening here? So now oxygen has 3 bonds. So what should be our next goal? Our next goal should be to neutralize the positive charge on oxygens. And we can do that by either bringing these 2 electrons here or either bringing these 2 electrons here. So because remember, epoxide is highly, since it's a 3-membered ring, it is highly strained. The bond angles are highly strained. It wants to pop open, right? Now on top of this, you have added a proton, which makes oxygen even more positive. And as a result, oxygen at this point wants to break open very, very badly. So here is what would happen. So the reaction here, it's gonna break, and simultaneously your nucleophile, which is oxygen, it would attack either this carbon atom or it could attack on this carbon atom. The question is where it would go. So let's discuss this in a second. So I'm going to draw the intermediate right here to show you what exactly we are doing. So let's say we have CH2C. Let's ignore that portion, CH3, OH. So let's look at this intermediate here. So you notice there is a positive charge here. So as soon as you develop a positive charge, what it wants to do is it will pull the electron right here. It will pull these electron towards itself. So now this bond here is partially broken. So if it is partially broken, now oxygen would have a partial positive charge instead of fully positive, where it's partially neutralized. Now this would cause also a partial positive charge. So this side, this is here, is a developing, it's not a fully formed carbocation. Just remember, it's a developing carbocation. Okay, so it's not a fully formed carbocation. So you have a developing carbocation. Now, what type of carbocation is this one? If you notice, this carbon atom is connected to only one carbon atom. So it is a developing primary carbocations, right? But what if instead of this carbon atom, the other carbon atom is a developing carbocations, right? So what if we have a scenario where instead of breaking on the left carbon atom, the oxygen decided to take the electron from the right side. So what if you have a situations like this? Okay, so instead of breaking on the left side, what if it decided it will gradually abstract these 2 electrons? So in this case, let's say if you have a dotted lines here, so now you have same delta plus on oxygen, but Look at the delta plus here on this side. Here, so this is a developing tertiary carbocations, right? So in this case, the electronic effect, which is generated by the stability of this developing tertiary carbocation, this is more likely to happen. So this reaction is slightly different than the basic conditions reactions with a nucleophile. So if you haven't watched that video, you should watch how in basic conditions the nucleophile goes towards the least crowded locations. But in acidic conditions, the electronic effect take over, where the carbon atom, the one that is connected to 3 other carbon atoms, is more likely to be attacked by a nucleophile. So in this case, our nucleophile will go towards this carbon atom and the electron would move forward. So the reaction here, the mechanism, it looks like an SN2 reactions here, although attack and break happen simultaneously, but in reality, the break happens first. Well, not entirely first, it happens slightly before the attack happens. So that's why you're developing a tertiary carbocation, and it's going to go towards the more crowded carbon atom, in this case, the tertiary carbocation. Not carbocation, tertiary carbon atoms. So let's recap again. In acidic conditions, the oxygen bonds, the oxygen and C bonds, it's going to break on the side that will generate a tertiary carbocation. But you are never making a tertiary carbocation, but the reaction does not go SN1. But by adding that extra proton, you're trying to develop a positive charge. Well, not you are, the molecule will decide which one is more stable. So that's where it would go. So just a rule of thumb, in acidic conditions, the nucleophile will go towards tertiary carbocation or tertiary carbon atom. So let's draw this one out. So this is, okay, so now let's draw the next molecule, what we will be making. So we will be making CH2, C, CH3, CH3, and our nucleophile is OCH3H. So oxygen has positive charge because it has 3 bonds. And what happens to our OH? It's right there. So and next thing is you just neutralize the positive charge on oxygens by adding some base or anything that could abstract a proton. So we just put B there. B stands for anything that can abstract a proton. And then we have our product, CH2, OH, C. Okay, I should have drawn this all better way. Since we are doing extended structure, I should draw. Okay, so we got our OCH3, and whatever that abstracted the proton will go away. So this is your final reactions. So remember, this reactions, although looks like an SN2 reaction, it is not a true SN2 reactions. It is in between SN1 and SN2. So which is why the nucleophile goes towards the more crowded atom, more crowded carbon atom, which is the tertiary carbon atom. So it's, if you have an opportunity to choose between primary and tertiary, you will always go towards the tertiary in acidic conditions. So let's do one last problem with the proper stereochemistry. So let's say you have the same problem we did in the previous example. So let's say you had here, so we got a methyl group there, and then we have an epoxide here. Okay, so here if we do this with H plus and same CH3OH, what would happen? So we got our oxygens that subtract the proton. So now we have, so we got our oxygens, and now oxygen is protonated. So that's become OH plus. Okay, so what's the next thing we're gonna do? The oxygens would pull two electrons. Either it could pull these two electrons or either it could pull these electrons. Now, because this reaction acidic conditions, our nucleophile is also gonna attack, but the reaction is not truly SN2 reactions or not SN1 reactions. So it's gonna attack towards the carbon atom that is a tertiary carbon atom. So this one here is connected to three other carbon atom, 1, 2, and 3. So it's connected to 3 carbon atoms. So this is a tertiary carbon atom. So the nucleophile attacks again, attacks on the tertiary carbon atom. Then let's talk about the stereochemistry. It'll attack on the opposite side of the oxygen. Opposite side of oxygens. So that's why it says it's not entirely a SN1 reaction. So it's still attacking on the opposite side of the oxygens. Okay. So in this case, what would be the product? So let's draw it out. So now oxygen here is to the top. It is still to the top. Okay, I will add the H here. Now here on this side, the incoming group, the OCH3, has come from the opposite side of oxygen. So opposite side of wedge is your dash. So I will add the dash. So that's OCH3 and H plus, and the methyl group get pushed up. So the methyl group that was here get pushed up to the from dash to the wedges. And final thing is your base would abstract the proton. So as a result, what you'll be making is, so stereochemistry wise, it's the exact same thing that we had before with the basic conditions. The only difference is the preferred location where it is attacking. Okay. OH. So that is the answers. All right. So let's stop the video here.